Hello everyone. Today we are going to start on shallow foundation and it is related to bearing capacity. So one of the problem that we can solve, that is 2024 set 2. It is the in situ percentage of voids. It is the percentage here. You should mind that it is percentage of voids, not the void ratio, of a sand deposit is 50%. That is, percentage of voids means it is the void ratio, porosity. So what is given here is porosity and equal to 50%. So percentage of voids of a sand deposit is 50%. The maximum and minimum densities of sand determined from the lab test are given to you. So what is given is the unit weight, that is maximum density, and minimum density. So maximum is given to you as 1.8 gram per cc and gamma minimum is given as 1.3 gram per cc. And the specific gravity is also given over here. So G is given to us. So G equal to 2.7. The relative density of the in situ sand is, we have to find out the relative density. So the simple formula for relative density is known to you, that it is given by E max minus E in situ void ratio of in situ soil mass divided by E max minus E minimum, whole multiplied by 100 in percentage you will be getting. So you will have to find out the relative density. Now, having got the value of N equal to 0.5, 50% it is, we can find out the void ratio E as N divided by 1 minus N. So if you calculate it, it is 0.5 divided by 1 minus 0.5, that is, it is going to be 1. So the void ratio is known to us now. So in situ void ratio, this is, or E0, you can say, it is in situ void ratio. So void ratio in situ, we have been able to calculate. Now, what is given is gamma max. The maximum unit weight, we know the relationship is given by G gamma W divided by 1 plus E minimum. When there is minimum void, then there will be maximum unit weight. And G is the void ratio, which is given to you as 2.7. And the unit weight of water, gamma W, is 1 gram per cc divided by 1 plus E minimum. Therefore, we can calculate the value of E minimum as 2.7 divided by gamma max, which is 1.8 minus 1. So if you calculate this, is 0.5. So E minimum is 0.5. So this value is known to us now. Now, from gamma minimum, we can find out the maximum void ratio. That is in loosest condition. This is in densest condition when the void is going to be minimum, and the maximum void will be in the loosest condition, which will be 2.7 G, gamma W will be 1, divided by 1 plus E maximum. So E maximum, here it will be gamma minimum. So gamma minimum is given to you as 1.3. So 2.7 divided by gamma minimum minus 1 will give you maximum. Same way as you have calculated. So let us calculate this. 2.7 divided by. This is going to give you as 1.076. We have to calculate up to 2 decimal places. So having got the value of Emax now, so Emax minus E in situ divided by Emax minus E minimum. So let us calculate by substituting the value in 1. So substitute in 1 to get RD. So relative density, we can calculate it. So now I have got Emax as 1.076. So I can calculate it. Minus E naught is 1. Divided by Emax minus E minimum. So divided by Emax was 1.076 and E naught is 1. So it is going to be 0.076 divided by. Now Emax is already known to us, this. So it is 1.076 minus E minimum, which is 0.5. So the answer for relative density is going to be 0.13 into 100 if you want to calculate in percentage. But it is rounded off to 2 decimal places. So the answer will be 0.13 relative density in decimal places. That's going to be the answer. In percentage, it becomes 13%. 13 point. And if you want to write it, this is 1319. So you can write it in percentage also, 13.19%. So either you can calculate in percentage. Normally relative density is expressed in percent. So that becomes the answer. So this is how you can calculate. This question I found out in shallow foundation and bearing capacity chapter, where you have to find out the relative density. Then the next problem that I would like to go further. is like this. Related to shallow foundation and bearing capacity. We will be considering the problem of 2024. A footing of size is given. It is a square footing, a footing of size B equal to 2 meter and depth D or DF equal to 1.5 meter is embedded in a pure clay bed. So the bed is pure clay, and the value of Cu is given as 40 kilopascal. Due to seasonal fluctuations, due to seasonal fluctuations of groundwater table, so the groundwater table is going to fluctuate from peak summer it will be the lowest to peak monsoon, where the groundwater will be at its highest position, or it will be at the shallow depth. And during peak monsoon period, the net ultimate bearing capacity of the footing as per Terjagi's bearing capacity formula or Terjagi's theory is the options have been given as remain same, that is no change, remain same. Then the next option is decrease, C increase, and the next is become zero. So these are the four options given over here. So you have a square footing like this embedded into the ground, all right? And this is the pure clay. Now, during dry season, the groundwater table will be going down, and during monsoon, it will be coming nearer to the footing. So, because it is pure clay, as you can see over here, the soil is pure clay. What do you mean by pure clay? Phi u, that is the angle of internal friction in undrained condition will be 0, and therefore, as per Tarjagi's theory, the net ultimate bearing capacity will be CNC. And now NC value, as you know, as given by Tarjagi, will be 5.7. So NC remains unchanged, and this will be Cu, which is given CNC. So the net ultimate bearing capacity means QNU. This is the formula. So NC is not going to change, Cu is not going to change, and there is no correction to water table here. Therefore, it remains same, no change. So it remains because the net bearing capacity is independent of water table, groundwater table correction, and therefore no change. Therefore, no change. You know the equation. QNU will be CU into NC plus Q times, that is the surcharge over here, Q into U, NQ minus 1 plus the third part. Now the NQ is going to be here 1 if it is pure clay. So NQ minus 1 becomes 0. So net ultimate, here you will be getting only one term, the first term. And N gamma is 0. So the third term becomes 0. So therefore, it is not going to be affected by the fluctuations of groundwater table, whether the groundwater table is here or during monsoon, it comes up near to the ground surface. It doesn't have any effect. There is no water table correction factor to the first term, and therefore it is going to be independent of the fluctuations, so it remains same. No correction is to be applied. So that is the answer. The next question we will be going now, which is asked in GATE 2023. So we'll be doing all the problems like pile foundation, which have been asked in GATE examinations, and we will explain the theory side by like we have explained the previous two problems. Now 2023, this is the set 2. You have a square footing. So square footing of size is to be found out. A square footing is loaded with 500 kilonewton. So the value of Q, the load which you have applied, or the allowable load or the safe load, that is being applied over the footing is given in the problem. The factor of safety is also given, and it is embedded into a ground where gamma t is embedded, is loaded with and is installed in the soil mass having phi equal to 0 in soil bed having phi equal to 0, and C is given to you as 25 kilopascal. The total unit weight is given as 19 kilonewton per cubic meter in this problem. So gamma T is also given to you, and the depth of footing df is given to you as 1 meter. So depth of the footing, and the shape and depth factors, shape oblique depth factors, you know the shape factor SC, SQ, S gamma. Similarly, depth factors are to be taken as unity, that is, it is going to be 1, and there is no effect, of groundwater table. That means the groundwater table is very, very deep. It is not going to affect your bearing capacity. Calculate the width of the footing in meter. Calculate the width of the footing in meter. So using Meyerhoff's bearing capacity theory, using Meyerhoff's bearing capacity theory. So you know the equation used by this, and the value of NC, because here phi is 0, it's a cohesive soil, will naturally be 5.14, and the value of NQ is going to be 1. So this is the problem. You can see how simple it is. The solutions can be easily found out. You have a square footing. This is the square footing embedded into the ground, and it is loaded with the load is 500 kilonewton, and the factor of safety is also given, and the value of C is given to you as 25 kilopascal, and gamma T is given to you as 19 kilonewton per cubic meter, and the depth of the footing from ground level up to here, the depth of the footing equal to 1 meter. So using Meyerhoff's equation, you have to use Meyerhoff's equation, bearing capacity equation, and for cohesive soil, the Meyerhoff's bearing capacity equation you already know how to calculate it, and it is given that the width of the footing in meter you will have to calculate it. So you can calculate the net ultimate bearing capacity, net ultimate bearing capacity, which will be given by C and C, shape factor, depth factor, inclination factor, plus the surcharge Q. Now it is net, so it will be NQ minus 1, and third term will be 0 because N gamma is 0. So for pure clay, you know that the bearing capacity factors are N gamma will be 0. So third term will not come into picture. Now this is the expression given by Merhoffs. So if you use it, you can find out the net ultimate bearing capacity. So net ultimate bearing capacity will depend upon C. So C is already given to me as 25. NC is already given by Meyerhoff. And these factors are 1. So now NQ is 1. So NQ minus 1 becomes 0. This term becomes 0. So therefore, I can find out Q safe. The safe, this is called the safe bearing capacity. This will be 1 upon factor of safety of Q Nu plus the surcharge, that is gamma times dF. So you can find out the net safe or safe bearing capacity. So net ultimate, and if you want to calculate the net safe, you can calculate the net safe also. So the net safe bearing capacity can be calculated very easily. Net safe. Then you need not add the surcharge. It will be simply net ultimate divided by the factor of safety, which is given over here as 3. So factor of safety being known to me, let me calculate this in kilopascal. Please calculate and find it out. So if you calculate this, you can easily calculate 25 multiplied by 128.5 kilopascal. This is the value of net ultimate. If I divide it by factor of safety, which is 3, I get net safe equal to 42.83 kilopascal. Having got the value of net safe, now I know the safe load, which is given as 500 kilonewton. So if you divide it by the net safe bearing capacity, you will be getting the area. Therefore, the area of the footing A is the required area of the footing. You can calculate it very easily as 500 divided by 42.83 kilonewton per meter square. So let's calculate 500 divided by this gives you 11.67 square meter. Therefore, for a square footing, it will be square root of area. Therefore, the width of the footing B in meter, we can calculate it. So, root of gives me 3.41 meter. So, this becomes the answer. So, you can see in one step, you can calculate the width of the footing. So, calculate the width of the footing in meter using Meyerhof bearing capacity theory. Easily you can do it. Let's go to the next problem. I will try to complete this chapter in the next video by taking as many problems as we can do it. But we will try to solve all types of problems so that in the examination you don't face any issues. So these are all related to shallow foundation and bearing capacity, and I hope you people are able to calculate. There is another problem in 2023 GATE examination, and that's related to the settlement of a footing. So, how the settlement of a footing is going to be affected, that the region of non-uniform, the region of non-uniform elastic settlement, non-uniform elastic settlement profile below a flexible footing So what is the type of footing is? It is a flexible footing resting on a cohesionless soil bed. So what is the type of soil? It is cohesionless soil. While subjected to uniform loading, is now so many options are given. The first option which is given is variation of friction angle, along the width of the footing. The second option, B, is given variation of soil stiffness variation of soil stiffness along the width of the footing along the variation of soil stiffness along the width of the footing. And the next option C is variation of friction along friction angle along the depth along the depth of the footing. And the last option, there are four options: variation of soil stiffness along the depth of the footing, along the depth of the footing. These are the four options. So this is the problem. You need to find out the solution. How will you do this? Simple one. It's a elastic settlement, SI, immediate settlement or elastic settlement of any flexible or any footing. You know it. What is the expression? That's immediate settlement of the footing that is on cohesionless soil. It is going to be immediate on settlement, and you know it. It is Q, intensity of loading into the width of the footing into 1 minus Poisson's ratio whole square divided by Young-Marsh loss of elasticity into the influence factor. This, you know it. Now, you have a flexible footing. So, a footing, the footing which is flexible. So, this is flexible footing and resting on cohesionless soil. So, this is resting over phi soil or cohesionless soil bed, and the intensity of loading is going to be uniform. The uniform loading over the footing. Now, the soil stiffness here at the edges, it's the phi soils are less confined, where the confinement at the center is going to be more. So the stiffness is going to change. And you know that mu is lateral deformation or lateral strain upon longitudinal X-ray. So you know that the value is going to change. So naturally, when it is deflects, it is going to deflect like this. So it is going to deflect like this. That means there is going to be minimum settlement at the center. This is the center line, and the maximum settlement of this flexible footing at the edges. At the edges, the confinement is going to be minimum, and maximum confinement to this cohesionless soil will be at the. So here the settlement is going to be minimum, and here it is going to be maximum. So this is the kind of situation that you know it, right? So this is the kind of situation. So if you see the option variation of friction angle, it has nothing to do with this. So this is out. Now variation of soil stiffness along the width of the footing. This is the width of the footing. Yeah, it is going to change. The maximum confinement is at this along the center line. So along the width, as you go away from the center line, the stiffness is going to change. So variation of soil stiffness along the width of the footing is the right answer. So you will have to choose the right answer. Had it been on a clay soil, it will be entirely different. Let's say this flexible footing is uniformly loaded. This is the uniformly loaded, but this is pure clay bed. Then it will be something like this kind of. So you will find that the footing is going to settle like this. Here the footing is going to settle like this. So footing settlement, you can find it out how it is going to settle and how the contact pressures, what would be the settlement. All those things you can discuss with the help of stiffness, soil stiffness. So soil stiffness is going to change. It's a cup shape. So it is going to be, if it is clay, the plate is going to bend like this in clay, isn't it? If it is phi soil, for C soil, for phi soil, it is going to bend like this. So the flexible footing is considered to be flexible, and whereas sea soil is also flexible, it's something like this. But here the stiffness is going to change, so it is like this. So all those things you can learn it. If it is not a flexible footing, but if it is a rigid footing, then also it will settle uniformly. And if it is a rigid footing, then on sea soil, it is going to be just reverse. And the footing is going to settle uniformly. It will not bend like flexible footing. And it is going to be just opposite of this. So here the answer to this question has been explained, that variation of soil stiffness along the width of the footing. So soil stiffness is going to change along the width of the footing. So it is going to vary. So these are some of the points that I wanted to highlight, and I will accelerate the pace so that the whole chapter on shallow foundation and bearing capacity, all different types of problems, using IS code methods, Tarjagi method, Mayer-Hoppe methods. Whatever questions have been asked, I'll try to deal with in my next video. So thank you, friends. Thank you very much. I hope the points which I have highlighted must be very, very clear to you. All the best.